this computer. Okay. History of mathematics. Let me just review. This is the book, Journey Through Genius, and we start with the Greeks. So the Greeks, and they really deserve a kind of a star because they introduced or invented or discovered. There are debates in the philosophy of mathematics whether mathematics exists in the real world and you discover it, or whether it's something that you create in your mind. But whether you use the word introduced or invented or discovered, what the Greeks discovered was the idea of proof. And this was really a huge leap forward in civilization, and we certainly haven't gotten beyond it. Today, we still use the paradigm of Greek mathematics. If you claim something is true in mathematics, you have to give a proof. Otherwise, you just have made a claim. And a long time ago, and one of the first results that was known is something called the Pythagorean theorem, which everyone learns in somewhere in school. If you have a right triangle and the sides have lengths A, B, those are the sides next to the right angle, and C is the hypotenuse, that the way we describe it today algebraically is A squared plus B squared equals C squared. So you have the two most famous right triangles, one with sides 3, 4, and 5, and you can check. 3 squared plus 4 squared is 9 plus 16 is 25, which is 5 squared. So that's this algebraic statement. Or if you take the triangle where one side is 5, the other is 12, and the hypotenuse is 13, you have 5 squared plus 12 squared is 25 plus 144 is 169, which miraculously is 13 squared. So this is sort of a modern way of writing the Pythagorean theorem. It's actually not what the Greeks did. The Greeks described mathematics often, not always, geometrically. And by geometrically, by a square, they didn't mean a number that you multiply by itself. A square for the Greeks was a square. That's a square. And so how would they describe the Pythagorean theorem? If you take the right triangle, where the sides are 3, 4, and 5, on the side of length 3, they made 3 the length of the side of a square. On the side of length 4, they constructed a square, which was a 4 by 4 square. And on the hypotenuse, they constructed a square. In this case, each side was of length 5. And for the Greeks, the Pythagorean theorem said that if you have a right triangle, say the 3, 4, 5 right triangle, the sum of the area of the two squares on the sides is equal to the area of the square on the hypotenuse. So the Greeks described the Pythagorean theorem geometrically. A square was a geometrical square, not an algebraic square. And we'll see in chapter, let's see, which chapter is it? Chapter 2. We will give Euclid's proof of the Pythagorean theorem, which is this geometrical theorem. And it's an extremely beautiful proof in geometry. I don't know how much geometry is still taught in high schools in America, anywhere. But this is an extremely beautiful proof in geometry of the Pythagorean theorem. And again, the point to remember is for the Greeks, the square was a square, a geometrical square, not a number multiplied by itself. Now, Euclid is the first truly great figure in Greek mathematics. And he wrote a book, actually a series of books called The Elements. There were actually about 10 books, maybe more, some of which have disappeared. They disappeared in the course of millennia. The first 5 or 6 books are geometry, and probably the 2 most often published and republished books in the history of the world are the Bible and Euclid's Elements. And you can still read Euclid's Elements profitably. It's really quite beautiful. The last few books have to do with algebra and number theory. But Euclid's Elements is really the start of mathematics, but it wasn't the start of Greek mathematics. And Euclid's Elements, it was almost like writing an encyclopedia. It was sort of a collection, systematized, of known results in geometry. So it's not that Euclid invented everything that is in his books. He certainly invented some of it, but some of it was already known. And it was rather like writing a big calculus textbook. You know, these calculus textbooks now weigh 10 pounds. They're 3 inches thick. But the person who wrote the textbook didn't discover the mathematics in it. The person is collecting the mathematics and putting it together in a coherent way. So even before Newton, there were certain results known. And one of the first has to do with an angle inscribed in a semicircle. So here is a circle. All right, I apologize always for my bad drawings. And this is the center. And here is the diameter. So the diameter divides the circle into 2 parts, and they're called semicircles. So this is a semicircle. And in that semicircle, you can choose any point on the circumference and draw the straight lines to the endpoints of the diameter. So this is called an angle inscribed in a semicircle. And let me see, excuse me 1 second. I'm going to see if I can find a compass. Let me just pause the recording. For one of the homework problems, you need a compass. And you can actually buy a compass for $2.59 at Staples or on Amazon. The trouble is, these are actually slightly better compasses, but no matter how good a compass you get, they're still pretty bad. And break. I just want to see if I could come up with a better way of drawing this picture, but it doesn't look like any of these 3 compasses is working. Let me just try this one, see if I can get it to work. All right, that's something like a circle. And this was roughly the center. So that's a semicircle on top. And I just take any point, choose this point, and look at the inscribed angle. Yeah. So we have, this is an angle inscribed in a semicircle. And we have the following theorem in Greek geometry, which preceded by 100 years or more Euclid, which says every angle, the angle inscribed in a semicircle, is a right angle. So that is in some sense a remarkable discovery. You take any circle, take any point on the circumference, draw the inscribed angle that is inscribed in the semicircle. So the endpoints, two endpoints of the angle are the ends of the diameter, and the third point is some arbitrary point on the circle, and it's always a right angle. And we're going to prove it. So the proof, now, when you prove things in mathematics, you don't start from the beginning. Suppose you've already proven the theorem, then you can use that theorem that's already been proven in your proof of a new theorem. So there were two facts about triangles that were already known. So two previous theorems. The first says the sum of the angles of the three angles of a triangle is always the same. It's a constant. So depending on how you measure, it's either pi radians or 180 degrees. And the second fact that was known has to do with what are called an isosceles triangle. So an isosceles triangle is a triangle with two sides equal. That means two sides of the same length. So that's the definition of an isosceles triangle. And the theorems about isosceles triangles says the base angles. What are the base angles? The base angles are the angles at the ends of the two equal sides. The base angles of an isosceles triangle are equal. Oh, and we can ask, what is a right angle? A right angle is an angle of pi over 2 radians or 90 degrees. Okay. So we have these two facts. The sum of the angles of every triangle is 180 degrees, and the base angles of an isosceles triangle are equal. So from that, we want to prove the theorem that every angle inscribed in a semicircle is a right angle. And the truly brilliant way of proving this is to draw an auxiliary line. So here we have the center of the circle. What is a circle? Circle is all points the same distance from the center. So all two radii of the circle have the same length. So let me draw the radius from the point on the semicircle that we want to show is the right angle to the center. So this red line, this takes some creativity. The red line wasn't there in the beginning, but we drew it. And this is the center of the circle. Let me call this O. This is the diameter A and B, from A to B. And this point, let's call it C, is the point on the circle that is the center, that is the angle of this inscribed. Actually, if I want to use the same notation in the book, which is a good thing to do, let me call this A, this B, and this C. So this is A. The diameter is from B to C through the center, and here's a point on the circumference. Okay. Now, if you look at this picture, we have the radius of the circle, plural of radius is radii. So you can see 3 radii in this picture. The line from O to B is a radius. The line from O to A is a radius. The line from O to C is a radius. And all these 3 radii have the same length. Now, if you look at this, you'll see that triangle OAB, that's this triangle. It's the triangle where the vertices are at O, A, and B, is isosceles, because OA and OB are radii. So these two have the same length. So OAB is an isosceles triangle, which means the angle, the base angles of this isosceles triangle are equal. So let's call this angle alpha and this angle alpha, they're the same. This is an isosceles triangle, the base angles are equal. And if you look at triangle AOC, that's also isosceles. OAC, because this is a radius and this is a radius. So in this triangle, let me give it a different color. In this green triangle, the 2 base angles, this is one, and this is the other. They're different from alpha, but this angle is beta and this angle is the same beta. So we have this picture, which you will find, by the way, in the book on page 7, exactly that picture, but not in color, but that's the picture. So what can we say? So consider the big triangle. In the triangle ABC, the sum of the angles of the triangle add up to 180 degrees. What are the angles of the triangle ABC? At B, the angle is alpha. At C, the angle was beta. And at A, the total angle is alpha plus beta. And the sum of the three angles of a triangle adds up to 180 degrees. But alpha plus beta plus alpha plus beta, that's 2 alpha plus 2 beta, or 2 times alpha plus beta. So 2 times alpha plus beta equals 180. Divide by 2, you get alpha plus beta equals 90. But what is alpha plus beta? Alpha plus beta is the angle BAC. That's the angle inscribed in the right triangle, in the circle, in the semicircle. That's what we wanted to prove. That's the end of the proof. So this is a beautiful proof that long precedes Euclid, that any angle inscribed in a semicircle is a right angle. And it uses some geometrical facts, again, that the Greeks knew, so they're allowed to use them, that the sum of the three angles of a triangle is always 180 degrees, and the base angles of a triangle, of an isosceles triangle, are equal. Any questions about that? So again, this is a history of mathematics course, and it's taught in the math department, not the history department, which means it really is a mathematics course. And these proofs are proofs you have to know and understand. And again, this is the sort of thing, if you were teaching geometry in high school, you could show your students this proof, right? It's not, it's something which they can and should be able to understand. Okay. Let's continue talking about Greek mathematics. The Greeks had, if you look, if you ever go, for example, to the Metropolitan Museum of Art, so you go in the main entrance, if you go to the left, there are several galleries of Greek and Roman sculptures. And if you look at Greek art, it's beautiful. And it involves a lot of symmetry. And you find these notions of symmetry in Greek mathematics as well. And there was some idea that the universe was perfect in some way and things were comparable. So if you had two lengths, there are two different lengths, the Greeks liked the idea that you could find some common unit of measurement. So you could divide this length into a number of small equal pieces, and you could divide the second length into a different number of small pieces equal, and they were the same. Each of these small pieces was the same. So, for example, this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This involves 12 pieces. 1, 2, 3, 4, 5, 6. Let me make this just different. So it's 7 pieces. So we would say that in some sense, these lengths are, the word is commensurable. So mensurable means measurable, and commensurable means they can somehow be measured in the same way or with the same unit. So you might say that the ratio of this length to this length is 12 to 7, right? This can be broken up into 12 equal pieces. This can be broken up into 7 equal pieces, and they're the same little pieces. And And it was just assumed that all lengths were commensurable. That is, no matter what two lengths you, and this, think of this if you like geometrically, you have two line segments and you break them up into small little line segments, little pieces. All the little pieces are the same length. And this, in this example, this involved 12 pieces, this involved 7 pieces. So this was like 7 times this unit of measurement, and this was 12 times the same unit of measurement. And the Greeks for 1,000 years believed that all lengths were commensurable. If you had any two lengths, you could always break it up into pieces, and each length was a certain integer multiple of pieces. And it was a huge discovery and very depressing to some ancient Greeks that this belief was false, right? So it's not unusual. Everyone believes something and it turns out not to be true. So what is true is the statement that not all lengths are commensurable. And this in itself is one of the great discoveries in mathematics. The simplest example is the following. Suppose you take a unit line segment, take any line segment, and then you can construct with a ruler and compass or however you like, a line perpendicular to it. And you can take a compass if you like, put the center here and one end here and draw the circle. So you can find a point on this perpendicular segment for this OA and B. So the length of OA is equal to the length of OB. Right? So you just have a right angle with the legs of the same side, and you connect them by a line. So now we have this right triangle, OAB. So let's say we call the length of the legs 1. So OA and OB, these each have length 1. So what is the length of AB? So in the notation we use today, if we were to call this X, by the Pythagorean theorem, we would have the length of the side squared plus the length of the other side squared is the length of the hypotenuse squared. And 1 squared plus 1 squared is 1 plus 1 is 2. So we get x squared is 2. So the length, in modern notation, the length of this side, x, is the square root of 2. So if you take an isosceles right triangle, this is isosceles, because these two sides are the same. If we call the length of the side 1, then the length of the hypotenuse is 2. If we call the length of the side 3, this would be 3 root 2, and so forth. But the ratio of the hypotenuse to the side is the square root of 2. And what is one of the great discoveries in mathematics is that the numbers, or the lengths, if you want to think of it geometrically, of 1 and square root of 2 are not commensurable. So let's go back and look at this example I started with. Suppose this is the line segment AB and this is the line segment CD. We would say that the ratio of the lengths AB to CD, this has 12 pieces and this has 7, is 12 to 7. So the ratio of this length to this length is like 12 over 7. 12 over 7 is a fraction. or what we call a rational number. A rational number is just a fraction. A rational number is a number that can be written as a fraction. And before the discovery that all lengths are not commensurable, the Greeks would have said that every number is a rational number. Any number you give me, you can always write it as a fraction. And this amazing discovery in the school of Pythagoras is that not every number is rational. So this great theorem, this is not, in every chapter of the book, there's something labeled a great theorem. This is not the great theorem in chapter 1, but it is a great theorem, is that there exist numbers that are not rational. They're called irrational. There exist irrational numbers, and in particular, the square root of 2 is irrational. And I will give you, this would not be a proof that the Greeks had, but this is a proof that we use today. And again, this is something you could tell students in high school, and if they were interested, they could understand it, whether or not they were interested, but they could understand it. Why is the square root of 2 irrational? So this is an example. So this is the theorem. Let me write it down again. Square root of 2 is irrational, which is the same way as saying, or the same thing, square root of 2 cannot be written in the form P over Q, where P and Q are integers, positive integers, actually, right? And the proof, so the proof depends on something which is fundamental in mathematics, the idea that mathematics is consistent, it's free from contradictions. So if you make a statement and you show that the statement leads to something that you know is false, then the statement that you started with had to be false. So that's what we call a proof by contradiction. So you assume something is true, you show that it leads to a false statement, and you conclude that what you started with couldn't possibly be true. So proof by contradiction. Assume square root of 2 is rational. So that means that the square root of 2 can be written as a fraction, a quotient of 2 integers, P over Q, where P and Q are integers. So if I just multiply by Q, you get the square root of 2 times Q is P. Oh, also I should say, if you can write this number as a fraction, this can be reduced to lowest terms. So P and Q have no common factor. If they had a common factor, you could divide it out. So you write square root of 2 as a fraction that's reduced to lowest terms. Multiply by Q, you get square root of 2 times Q is equal to P. Square both sides. When you square the square root of 2, you get 2Q squared, and that has to equal the square of the right side, which is P squared. So 2Q squared equals P squared. Now, some numbers are even and some are odd. A number is even if it's divisible by 2. 2Q squared is even because it's a multiple of 2. So p squared is even. And again, you know, if you multiply 2 odd numbers, you get an odd number. If you multiply 2 even numbers, you get an even number. So if p squared is even, that means p is even. And what does it mean for a number to be even? It's a multiple of 2. So p is...
Wi-Fi online.
Sorry? You have a question?
No, I'm sorry.
So p is even, so it's 2 times r for some integer r. So we have 2q squared is p squared, but p is 2r, so this is 2r squared. If you square 2r, you get 4r squared. So 2 squared is 4r squared. If you divide by 2, q squared is 2r squared. This is an even number. So q squared is even. And as we just saw, if the square of q is even, q is even. But now we have a contradiction because p is even and q is even, but p and q have no common factor. That's a contradiction. So the contradiction came from our initial assumption. What was the initial assumption? The initial assumption is square root of 2 is rational. That led to a contradiction. So we conclude that the square root of 2 is irrational, is not rational. And that's the proof. And this, with 100% certainty, is going to be something that appears on a midterm or a final, because there's no way you can take a course in the history of mathematics and not be able to show that the square root of 2 is an irrational number. Any questions about this? All right. Let's look at another problem in elementary or in early Greek mathematics. And that is what we might call computing the area of geometrical figures. So you might have a square. You might have a rectangle. You might have a triangle. You might have a figure which is a polygon. It's just a figure whose sides are straight lines. Polygon. You could have a circle. You could have an oval or an ellipse. You can have something more complicated like something that looks like part of a moon. It's called a lune because it looks like a moon. Lune means moon. How do you get a lune? So one way of getting a lune is you have a circle and you have another circle, and this part out here, which is what you get from intersecting one circle with another, that's called a lune. Okay. So the Greeks were interested in computing the area of geometrical figures, but they didn't mean by that a number. Right? So let's start with the square. So the basic unit of what we might call measurement is the square. So let's say the square is something the Greeks thought they understood. And what does it mean to compute the area of a rectangle or any other geometrical figure? So computing the area of a geometrical figure means, for the Greeks, constructing a square with the same area as the figure. So what would it mean to compute the area of a rectangle? It would mean to construct a square and to prove that the area of the rectangle was equal to the area of the square. And this problem of computing areas is called the problem of quadrature. This means computing, or a better word would be constructing a square with the same area as a given geometrical shape or figure. Geometrical body. And what does constructing mean? In Greek geometry, it means using a straight edge and compass. A straight edge is not a ruler. It's not a ruler. A ruler, this is a ruler. It has marks on it. 1 inch, 2 inch, 3 inches, and so forth. This is a ruler. The Greeks were not allowed to use a ruler. They could only use a straight edge, which would be like if you erased all the numbers from this and it was simply a straight edge, no numbers. So they couldn't measure something with a ruler. They had no rulers. Rulers weren't allowed. The only two tools they were allowed to use in geometrical constructions were the straight edge and a compass. If you had any 2 points with your straight edge, you could draw a line through those 2 points. And the line went on forever in both directions. So they could draw a line through 2 points. If they had 2 points, they could think of one as the center, and with the compass, they could draw a circle whose radius was the line segment between the 2 points. So it's all points equidistant to this point O, which we call the center. So with the straight edge, they could draw a line through 2 points. With the compass, they could draw a circle with any one point as the center and any other point as a point on the circumference. These were the only geometrical tools they were allowed to use. And the first construction we're going to show, the first example of quadrature, and you might think this is the easiest thing to do, is compute the area of a rectangle. And you can't say, well, the area of a rectangle is its length times its width. What you have to do is show that you can construct a rectangle whose area is the same as the area of the square. Now, how you prove the two are the same, we're going to use the facts we know, like the area of a square is or the area of a rectangle is the height times the width, but we can only use that to prove that our construction is correct. Right? So let me start by drawing a rectangle. So here's a rectangle. And again, I'm going to follow the notation in the book. So this is on page 13. So this is the rectangle BCDE. And a rectangle means it has four sides, it's a quadrilateral, and each of the four angles is a right angle. And the problem is to construct a square with the same area as this rectangle. Okay. So we only can do constructions that are possible with ruler, with straight edge and compass. So for example, with my straight edge, I can take the line from B to E and extend it. And I can take the line from E to D and extend it. So this is also a right angle, of course. Then I do the following. With my compass, I can draw part of a circle where the center is at E and the radius is ED. So if I draw that circle, it's going to intersect this line at some point, and I'll call that point F. So ED and EF have the same length. Okay. Any question about that? All right. I took my rectangle with my straight edge. I extended these two sides. With my compass, I can draw this circle, but I really just care about where it crosses this horizontal line. I call that point F. And now I have the line from E to F. And I want to, now with a straight edge and a compass, it's easy to construct the midpoint of any line segment. So if I take the line from B to F, I can find its midpoint. I'm going to do it by cheating, which is to say, just do it by my eye. So I construct the midpoint for this G. So G is the midpoint of the line segment from B to F. Okay. And then with my compass, I'm going to want to draw, see if this is about right. Yeah, it's not bad. I draw this semicircle. Which I can't do with this compass, which is broken, but. So I draw this semicircle, which looks something like this. So that's the semicircle where the center is a G and the radius is the distance from G to B or from G to F, the same thing. And the point where the semicircle crosses this vertical line, I'll call H. So, all right, so let me just go through the steps that I used to so far. I started with a rectangle. It's this green rectangle. And I want to construct a square whose area is exactly the same as this rectangle. So I extended the top of the rectangle, that line, and I extended the right side vertically, this line. And then with my compass, I could find the point F to the right of the rectangle, where the distance from E to F was equal to the distance from E to D. And then between the points B and F, I found the midpoint, and I constructed a semicircle whose radius was BG. And that intersects this vertical line at a point H. And I claim that if I construct the square whose side is from E to H, that square will have the same area as my green rectangle. So let me try to do that. It's a square, which is going to look something like this. Let me call this point K and this point L. And this is a square. Let me color that square different color, blue. So I claim that the area of the rectangle that I started with, the green rectangle, BCDE, is equal to the area of the blue square, EHLK. I claim these have the same area. And that's what, so from that point of view, I can say, as the Greeks would say, I've just computed the area of the rectangle because I've constructed a square with the same area. And how can we prove that? Okay, so this is a right angle. So this is a right triangle. Let me call this side B, this side A, and this side A. Okay? So this right triangle has legs B and C and hypotenuse A. Now, this is A. So this is A, because remember, this is a circle, center at G. So this is A, this is A. From G to F is also A. If this is B, then this has to be here, A minus B, because these two pieces add up to A. So that's A minus B. A minus B, EF is the same as ED. So this is also, ED is also A minus B. So what is the area in modern notation? What is the area of the green rectangle? It's the length of the side BE times the length of the side ED. From B to E is A plus B. From E to D is A minus B. A plus B times A minus B is A squared minus B squared. So in algebraic language, the area of the green rectangle is A squared minus B squared. What's the area of the blue square? Well, the side of the square is C. It's C squared. This is a right triangle. In this right triangle, B squared plus C squared is A squared. A squared is B squared plus B squared, C squared. So C squared is A squared minus B squared. So the area of the blue square is C squared, is A squared minus B squared. And a miracle has happened, we're done. The area of the green rectangle is A squared minus B squared. The area of the blue squared is blue square is A squared minus B squared. They're equal. So this blue square has exactly the same area as the green rectangle. So it's worth spending an hour or whatever it takes to go through this proof very carefully, because it's quite a beautiful proof in Greek geometry. So we have solved the quadrature of the rectangle. Given any rectangle, we can construct a square with the same area. Okay. Any questions about this? All right. What about other geometrical figures? What about quadrature of a triangle? So let's take a triangle. Not a right triangle, just any triangle. So here we have a triangle. Let me call it BCD. From D, if I drop a perpendicular to the base, what's the area of the triangle? Well, let's do something different. I have my triangle BCD, drop this perpendicular, I can find the midpoint. Let's call this F. So you drop the perpendicular from D to the base, it hits the base at E, and the midpoint of DE is F. So DF is equal to FE, right? This equals this. Now, here we have the length BC. Here we have this height, F. I can draw a perpendicular with the same length as this. So here we have a triangle. Here we have a rectangle. I claim the area of this rectangle is the same as the area of the triangle. What is the area of the rectangle? The area of the rectangle is half the base times the height. Or if you like, the base times half of the height. What's the area of this rectangle? It's equal to the base, which is the same as the base of the triangle, times the height of the rectangle, but the height is half of the height of the triangle. So this triangle and this rectangle that I just constructed have the same areas. So I start with the triangle. I construct a rectangle with the same area, but by the process we just finished, I can then construct a square with the same area as the rectangle. So the square has the same area as the triangle. So we've solved the problem of quadrature of a triangle. Right? If I can construct a rectangle with the same area as the triangle and a square with the same area as the rectangle, then the square is the same area of the triangle. Okay. Now, what about more complicated geometrical figures? Suppose I take a quadrilateral, four-sided polygon. Now, how can I construct a square with the same area as the quadrilateral? Well, this quadrilateral, if I draw this line, is a sum of two triangles. Right? Well, triangle A and triangle B. I can construct a square with the same area as the triangle. And I can construct another square with the same area as triangle B. So here we have a quadrilateral, a geometrical figure with four straight lines as its edges. It divides into two triangles. I can construct a square with the same area as each triangle. What about the two of them together? So I can construct a right triangle where one side, let's say this has length A, this is length B for the sides. If I take a right triangle where one side is length A and the other side is length B, look at the square on the hypotenuse. The square on side A, that's the square capital A. The square on side B, that's the square on side B. This side has area A plus B. That's the Pythagorean theorem. The square of the hypotenuse is the sum of the sides of the area of the legs. So I can actually add these two triangles. Each triangle corresponds to a square. From those squares, I can construct a square whose area is the sum of these two, which is the sum of the quadrilateral. And I can continue to do that for any quadrilateral of this sort of general size. Here's a polygon, not a quadrilateral, but I can write this as a sum of four triangles. So for these two triangles, I can construct a square with the same area as these two triangles. I can construct a square with the same area as this triangle, and with my Pythagorean theorem trick, construct a square which is the same area as these three triangles together, construct a square with the same area as the fourth triangle, and again with the Pythagorean theorem trick, construct a square with the same area now as all these four triangles together. So we have now the quadrature of any polygon. So for any polygon, this convex polygon as I've drawn it, we can construct a figure with the same sides. So this basically deals with any geometrical shape whose sides are straight lines. But what about curved figures or curved shapes, like a circle? Can we square a circle? That is, given a circle with straight edge and compass, can you construct a rectangle? Sorry, can you construct a square with the same area? Now, this was a problem that the Greeks could not solve. In fact, it took approximately, you have to be a little bit patient sometimes in mathematics, it took approximately 2,000 years before anyone could solve the problem of squaring the circle, right? So to construct a square with the same area as the circle is called squaring the circle with straight edge and compass. And it was proved in the 19th century, squaring the circle is impossible. So there's some problems in mathematics that have no solution. Well, actually, we already saw one. Here's the problem. Write square root of 2 as a rational number. That's impossible. Construct a square with the same area as a circle using only a straight edge and compass is also impossible. So there's a huge difference between quadrature for a figure whose sides are straight lines and quadrature for a figure whose sides are curves. But it was an amazing result, and this is what is, in every chapter I said there's the great theorem. The great theorem in chapter 1 is a mathematician, a Greek mathematician named Hippocrates. He squared a certain lune. Remember, what is a lune? You can take a circle, take another circle, and an area cut out between the two. That's called a lune. And for a certain lune, Hippocrates was able to construct a triangle with the same area. And once you can construct a triangle with the same area, you can construct a circle with the same area. So this is the great theorem in this chapter. And the theorem uses one, again, you're allowed to use theorems that were previously known. So the quadrature of the lune of Hippocrates' lune, it's not any lune, uses 3 preliminary results. One is the Pythagorean theorem. ABC. So the square on A plus the square on B has the same area as the square on C. The second is the theorem that says an angle inscribed in a semicircle is a right angle. And the third, so we already proved that, and we already saw the Pythagorean theorem, though we haven't proved it yet. And the third has to do with the ratio of the areas of 2 circles with different diameters or radii. So this is a circle of diameter D, and this circle has diameter capital D. What is the ratio of the area? So let's call this, or whether we use the circle or the semicircle. Let's look at the semicircles. So the area, call this circle 1, and this circle 2. So the area of semicircle 1 divided by the area of semicircle 2, the ratio of those areas is like the ratio of the squares of the diameters, right? So this also is a fact that the Greeks knew. Well, using modern notation, it's easy to prove this because recall that the area of a circle of radius r, which is the same as pi r squared. Pi r squared, because the radius is half the diameter, so that's pi times the diameter over 2 squared, or pi d squared over 4. So this is a radius r, or diameter d, call this A1. And for the circle with diameter capital D, the area of the circle A2 would be pi capital D squared over 4. So if you look at the ratio of the areas, the area of circle 1 divided by the area of circle 2, that's pi d squared over 4 over pi capital D squared over 4. The pi over 4's cancel, you just get d squared over capital D squared. So with modern notation, this is an easy thing to verify. But in any case, this was something known to the Greeks in that they used that if you have 2 circles or 2 semicircles, the ratio of their areas is like the square of one to the square of the other. Okay. All right, so we've covered a fair amount of material today, roughly half of chapter 1. And this is a good point to stop because the next thing we're going to do is prove the great theorem, the quadrature of the lune by Hippocrates. And we'll do that on Wednesday. Any questions about anything that we've done so far? Someone asked in the chat how many homeworks will be given and will be graded. So there's basically a homework every week, and you write out the homework, convert it to a PDF, upload it to Blackboard. The first homework is typical. There are I think there are 9 problems, and the homework is to do 6 of them. But if you do more, then you can get some extra credit.
Professor,
Yes.
when you when you grade the homework, do you write corrections or do we go over the corrections in class?
I can't do corrections because I'm looking at a PDF file. No, I just look to see whether you've done a reasonable amount of work. They're graded in that sense. That is, if you've done a reasonable amount of work and you turn the homework in on time, you get full credit. And if there are 6 questions and you've only tried 1, you might get you'll get partial credit, but you won't get full credit. If you have to turn the homework in late, unless this is abused, there's no penalty. I'd rather you do the homework late than not at all. But if you have a question about the homeworks, then you should ask me at the beginning of class, because I start every class by asking if there are any questions. Or you come to one of the Zoom problem sessions and you ask me there. And if you can't make one of the Zoom problem sessions, send me an email and we can just work out a time just for you where we can meet on Zoom. So there should be more than enough opportunity to ask for questions. And some of the homework problems I'll go over in the lectures because they're interesting and it's useful to know about.
Okay, thank you.
Okay. And again, as with all these lectures, so long as I don't forget, I record them. There is a YouTube channel. There's a YouTube playlist in my channel, which has the unoriginal name of Nathanson Math Lectures. All the information is on Blackboard. And I normally post each lecture on Blackboard, on YouTube, as soon as it's compiled, so within a few minutes or 15 minutes or so after the end of each lecture. So you can always go back and look at the lectures again. Okay. Anything else for today? We're stopping a few minutes early, but I think we've covered enough for the first day of the class. Okay, well, see you Wednesday morning. Bye.
Bye, Professor. Have a good day.
Bye bye. Thank you.
Mhm.